Hi everyone, my name is Ujjwal, and today we'll be learning about convolutional neural networks, also known as CNNs. So, we have a brief idea of how neural networks work in general. If not, I would highly recommend watching my previous video on neural network. Link will be in the description. So, let's move on with convolutional neural network. Before we go ahead and learn how it works, we'll think of this, we'll go with the situation as of now. Assume you have an image, containing a small house and some kind of sun or clouds or something. So now, how would you try solving this solution wherein your model needs to identify whether there is sun present in an image, or basically trying to solve a problem wherein you have to identify whether it's day or night? How do you try to solve this? Well, based on our current knowledge, what do we know? A neural network is something that can take in data in its one-dimensional format. For example, here is a very simplistic neural network connected, our input layer. We don't have any hidden layers in this case, and we have our output layer. So we given x1 and x2. What is x1 and x2? Before passing in x1 and x2, this is how it will be located, or this is how it will be structured in our array. Assume this is our final, assume this is our variable inp input. So this is how it will be structured. So, and you pass it into your neural network. So this is fine. Now, how would we process something like an image? So that's where we have to think about how the images are observed or understood from a computer's perspective. So if we go into the basics, an image is basically a combination of pixel values. So if you look at each pixel value, assume I draw a zoomed in version of some part. Assume I take this part over here, I draw the zoomed in version of it and divide the image into 4 parts for simplicity. So here the pixel value will be somewhere close to uh, uh, zero point 0.3. I'm just giving random values for now, between 0 and 1. And here, since there is sun, it will be very close to 1, 1 being the highest, which means it's brighter spot. And this will be somewhere close to 0.5, and this is assume this complete one. So what are images? Images are basically pixel values, right? So when you break down an image into its pixel values, so we get a two-dimensional array of multiple values. So you'll have so many values in a two-dimensional array. But how do we use neural network? How do we use this neural network and a two-dimensional array as our input data to help with this? Well, let's look at it this way. We have two options over here. Let's discuss the first option. First option, assume we have a 4 by 3, or we take a 4 by 4 image. What do you mean 4 by 4 image? When I say 4 by 4, it's an image which has 4 pixels on each sides, or it's like a height of 4 and width of 4. So when I say 4 by 4, we have total of 16 pixels. So what do we do now? One thing that we can do is we can push everything to one dimension, or basically reshape in such a way that we just have a single dimensional image. So when I reshape this, what will happen? I'll have a very big array with 16 values. So I'll have here x1, x2, x3, and so on up till x16. So this will be my input x. So similarly, I'll need to have like 16 neurons in my input layer, so on. So assume that's 16 neurons, and so on and so forth. Finally, I'll have like 1 neuron or 2 neurons, or how many ever neurons at the final output layer. So this is how we could do based on our current knowledge. And there's a second option which we'll discuss later, but there are certain drawbacks with this solution. So let's discuss them one by one. So what's the first issue? Let's go back to our previous example wherein we had a small house and sky with a sun in it. So now assume I were to reshape it in this format. if I were to reshape it in this format, we would lose all the spatial features, because when we saw this image, we were clearly able to make out that sun was in the top left corner and the house was in the bottom right corner. But when we see this image, or this is not an image at all in the first place to a human eye. So when we see this array, we are not at all able to make out what represents a sun and what represents a house and what's happening, stuff like that. So we lose all the spatial features. Secondly, the number of parameters, the number of model parameters per se, the number of model parameters increases drastically, because now we had a simple 4 by 4 image. Now we have to process, of course, when we reshape it, we have a length of 16, right? So we have to process all these 16 inputs. So our number of neurons increases in the first input layer. So that leads to more number of weights and biases and interconnections, since each neuron is connected to every other neuron in its next layer. So the dense architecture is more has increased a lot. So that's why it leads to more model parameters, which leads to a slower training, or heavily computed training, wherein your model demands more resources, and at the same time it might not learn that well. So these are the issues, but this approach still works. It works, but it's not very efficient and won't understand the image very well. So let's move on to the second solution, which is a new architecture called convolutional neural network. Now let's take a simple 2 by 2 image, or let me not call it an image, let me just draw it over here for now, and let me draw an image of shape 3 by 3 for simplicity. So this is an image 3 by 3. Assume there's an image drawn over there. I'm keeping it blank for now, and assume each box represents a pixel value. So let's think of this pixel value as 1, then this has 2, this is 1, 3, 4, 6, 3, 1, 2. These are just random numbers. Well, of course, an image will have its defined pixel values, but I'm keeping it random for now. Now, let's try to analyze how we can understand this image without having to reshape it, or like squeezing everything into like one single dimension. We want to keep it in 2 dimensions. How do we do that? So what we can do is we can analyze the image in patches. We can start analyzing the image in patches. So when I say patches, so you can keep the patch size as how many ever you want. So assume I keep a patch size of 2 by 2. So here we assume this is my patch. So this is one patch that I've drawn here. So it's a patch, and this will also have random values like 0.3, 0.1, 0.6, 0.7, something like that. So when I have a patch like this, I need to analyze this image by every patch. So let me just draw the patch on top of the image. Assume I just look at these first 4 values in the beginning. Assume I'm just placing this patch over here. So what happens when I place that patch over there? Let's just multiply the values. So it becomes 0.3 into 1. So it becomes 0.3. Then this is 0.1 into 2. So it's just 0.2. 0.6 into 3. So 1.8. 0.7 into 4. 2.8. So we have these 4 values. So what happens is these 4 values will be added all together. So then you'll get a new value. Assume I write it as x1. So what happens is you place your patch on the image, multiply the values and add them. So you get a different value. Then after this is processed, you still have to look at the other part of the image, right? So what do? You move this patch to the next step. So it goes right. So it's like going one step to the right. Then it analyzes that patch and gives you another value, x2. So then since this part is done, it has nowhere to go right. So what does it do? It comes one step down. So it goes here. It goes to the bottom left, analyzes it, and gives you x3. And again, similarly, it would move one step to the right and give you x4. So what essentially has happened is we went from a 3 by 3 image. So we went from a 3 by 3 image by using a 2 by 2 image, or this is a 2 by 2 patch actually, 2 by 2 patch, which gives us what? If you see here, we got x1, x2, x3, x4. By combining the values using the patch, we got a 2 by 2 image. So when you see, what happened is it tried compressing a 3 by 3, basically 9 values, into 4 values. So what would happen if you had a bigger patch size? When I say patch size, assume instead of 2 by 2, you had 3 by 3. If you had 3 by 3 and you tried placing that patch on the image, it would cover the entire image. And when you multiply each element one by one and add all of them, you would just get x1. That's the only value. What I'm trying to say is, if you had an image of 2 by 2 and if you had a patch also of 2 by 2, this is your patch and this is your image. And if you placed it on top of this to view it in patches, but it ended up covering the entire image, you would just multiply each pixel value one by one, which would end up giving you only x1. So it will become a 2 by 2 image into 1 by 1. So you would just end up compressing a lot. Here we compressed from 3 by 3 to 2 by 2. So what essentially happens is, if you have your image I, it goes through one convolution operation. It becomes I1, for example. Then another convolution operation, it becomes I2. Of course, the shape can either remain the same or it can go down. So what essentially happening is, it is trying to absorb essential features. So it will only retain important features over there. But what do we know here is, this is fixed because you can't change your input image. So how does the CNN model learn now? Well, going back to neural networks, what we knew is, in neural networks, the things that can change are weights and biases. Weights were basically the W1, W2, and so on. And the biases were B1, B2, and so on. But in convolution neural network, it's very similar. If you see here, what we can modify here such that it tries learning in each step is, one, you can change the shape of your patch. Yes, if you have a bigger patch, it will compress a lot. If you have a very small patch, it might not compress at all. You need to analyze what should be the patch size. So that's in your hands. But what happens during the training, wherein you don't have any control, that's where these weights are changed. This 0.3, 0.1, 0.6, and 0.7, these are convolution neural network weights. So basically, instead of having weights between neurons, this is how the weights are placed here. So these are random numbers to begin with in the beginning. So as and when the model learns again and again, it learns to change these numbers such that when this is multiplied with 1, 0.1 with 2, and so on, it gives you a number or another image like here in the bottom, such that it is a better representation of the image. It will try to extract only required features. So here also we have the same weights and biases, but they are structured in a different way. That's it. So it is just used to extract important features, extract required features, I should say. Extract required features. So this is how CNN works in general. So to recap, so you have a image, let's take 3 by 3, and you have a patch of 2 by 2. Also, there's a terminology for patch. When I say it as patch, people usually call it as kernel or a filter. So you would be hearing words like kernel size or filter size. So assume this kernel, you place it here, you multiply the numbers, you get a new value x1. Then you move your kernel one step or how many ever steps, that is based on your choice. Then you multiply the next 4 values, get x2. Then you bring it down since you can't go any more further towards right. Multiply these 4 values, get x3. Move right, multiply all the 4 values, get x4. So you converted 3 by 3 into 2 by 2. Similarly, if you keep performing this with a different kernel size in the next operation and so on and so forth, you might end up with a very small image, or you might do some other kind of analysis further on. So this is the basic working of a convolutional neural network. And when I say it moves one step, the name given to its movement is called a stride. Here, if it's moving one step, the value of stride is 1. If it's moving 2 steps, assume I draw a bigger image. So let's not worry about the number of rows, let's look at the number of columns. And I have a 2 by 2 filter kernel or a patch 2 by 2. So if I keep the filter here, so let me just change the color, and if I keep the filter here, so this is how it does the first operation, we get x1. Then if I keep my stride as 2, assume it's not 1. So instead of going, let me change the color, instead of going to where the yellow patch would have been, it will actually go over here. So it skips two steps. Assume this is your point of reference. Instead of going one step, it goes to the another step. So it takes 2 steps and then performs the analysis there. So what essentially happens is, if you have higher stride values, then you might lose on some features. You might lose some features because it's moving faster, and you might end up with a smaller image dimension at the end, smaller dimension, because if you're not traveling to every part and increasing the x1, x2, x3 counts, assume if you were to go one by one, you'll have this as 1 x1, then the yellow one will be x2, again the red one will be x3, then finally one more step will be x4. So you have 4 values in, basically you have 4 columns here. But if you were to take the stride as 2, you would go on the first red patch, then secondly you would move on to the second red patch. So you'd end up with only x1 and x2, and since you can't take 2 steps forward, you'll just go down. So you might miss on so many pixels, and the final image dimension will also reduce. So you'll lose features, and this dimension will also be smaller. So this is what is the utilization of stride in our use case here. So we have stride, we have kernel, and we have our image size. Now let's look at one more feature that we have control over. Assume you don't want to shrink the image size as and when you go on. Let's draw a 3 by 3 image, and we have our kernel which is 2 by 2. Now we know what happens if we go through the convolution one by one, we get a 2 by 2 image at the end. But what if we don't want to do that? So let me draw an external pixel cells over here. Assume I'm drawing external pixel cells. So what is happening here is, now the original size of the image is same, but just before passing or doing the convolutional operation, we just increase the pixel size. Now we just increase the image size, I should say. Now assume it was 3 by 3 in the beginning. Now what happened, since I added external cells or external pixel values at the end, what happened? It became 5 by 5. So now if I do the convolution operation, so let me just take red to represent the convolution happening. It multiplies these 4 values, gives me x1. Next one, over here it happens, convolution happens and then gives me x2. Then finally over here x2, x3, and then x4. Then similarly it goes down, we get x5, x6, and so on. So what happened is, here the image didn't shrink. So what is this external cells or pixel values that I've added? That is called as padding. So if you can add external padding with empty values, when I say empty values, it's usually 0. So you're adding 0 valued pixels here, which is basically black pixels. So you're adding all of these here to not give any importance to it, because when you multiply anything with it, it just becomes 0. So you're just making sure the final dimension remains the same and it doesn't shrink very quickly. So you don't want the image to shrink so that you might lose features later on down the line. But there's a hidden advantage to using padding. So the main actual reason to using padding should be this one itself. So assume you have an image wherein you know there are some important features present at the corners or at the borders mainly. Assume there are some hidden features or important features that you want the model to learn. So what happens in regular convolution is, let's go through the regular convolution again one more time, and my patch size will be constant 2 by 2. So it goes through here once, here again, then here, then finally here. So what happened is, at every convolutional step, if I were to redraw the image to give a better understanding, this pixel on the very top left was only seen once. The middle pixel, the second pixel over here, was seen twice by the same patch but at two different places. This was seen twice. This was seen once. And here this pixel was seen twice. This was seen four times actually, because every patch saw it at every iteration. Then this was seen twice, then this one, then two, and then one. So this is how it was seen. Now what if our image contained an important feature at these corners? What would happen at that time? So we would just see them once and then forget about it, or at least the model would see it once and then forget about it. So to avoid that, we add extra padding over here, so that when you perform convolution here, it not only sees once because of the first iteration, it also sees again because it's overlapping again when it's moving one step at a time. So that's the entire purpose of padding. That would increase the count of the pixels seen even at the corners. So that would lead to better extraction of the features from that image. Okay, let's try to understand the practicals of how convolution neural network works on a sample image. So here I've loaded in a sample image. So this is how the image looks like currently. So I'll just create a convolutional layer. Uh, so with kernel size 3. So if we see before applying the convolution, currently the image size is 359 by 640 by 3. So the first number represents the width, then the height, or height and width. Then the final one represents the number of color channels. Since this is a color image, here 3 represents RGB. So each pixel value is actually 3 different values. So instead of having a grayscale image, this is containing just 3 different values. So you'll need to apply convolution for all those values. So I'm currently using TensorFlow. It's a Python library and a framework which was used to perform deep learning computation. So I've just created a layer as a conv2d. Conv2d stands for convolution on a 2D image. So this is our convolution layer. So I'm just converting my image into a float data type because it's easier for operations. Then I pass my image into convolution layer. Then I get my output. So if you see the shape of the output is a bit different. In the beginning, if we see the original image, the shape of the original image, it was 359 by 640 by 3. This became 357 by 638 by 1. So there is some kind of shrinking or compression happening. So when we look at the image, so this is what it was able to extract. So it extracted some kind of the lights and the background here and there. So this is what it has extracted. So here is a comparison of how it is. So this is before convolution and this is after convolution. Now what happens is, the weights that we saw in the patches or the filters is assigned randomly every time, right? So if I were to run the convolution operation again, so what happens is the weights are assigned in a different way. So when we apply the patches one by one over here, it moves one step at a time. So it extracts in a different manner. If I were to run it again, it extracts it in a different manner. It's all dependent on how the weights are initialized in the beginning, the weights which are present in the patches or the kernels. So that's what matters. And then as and when you train the actual model, that's when it will try to fix those weights. So here is one more view of understanding convolution. So this is a web page called CNN Explainer. I will put it in my description. So let's try to see how convolution operation works on a particular image given here. So when you go to this website, you can actually read about everything over here, and I do encourage everyone reading this. It explains what an input layer is, convolution layer is, and so on. So let's just click on one image over here. So let's click it again, and we can see what's actually happening here. So let me just zoom in. So when I click play over here, you can see the small kernel over there, which is of 3 by 3, is moving one by one step at a time on this image of 64 by 64 and extracting certain features. You can see here, this is the kernel. Let's see what that is. So yeah, these are the kernel weights, 0.14 minus 0.03. Those are random kernel weights. It's constant everywhere because the kernel is same. The above box over here, that's the actual pixel value at what it is looking at. So when you keep multiplying, you get a single value. So all these 9 values are being compressed into one value because it's a 3 by 3 kernel. So when you compress it, finally you can see from 64 by 64 we went to 62 by 62. So this is how convolution works. So similarly, as and when you keep going forward again and again, you can see in each step over here. So you can see as and when it goes forward, it learns better and better. So at one point it was 30 by 30. Then by using the weights and multiplications of each pixel value, it compresses into one value, and then it became 28 by 28. Then as we spoke about the things that we can control, this is what we were speaking about back then. These are called as hyperparameters, the things that you can control. Now assume you were to increase the size of your input image itself. So it is 5 by 5. Then padding is something that we add on the exterior of the image to make sure it analyzes the corners and keeps the output size a little bit bigger than what it is right now. Then kernel size is the size of this smaller patch which is moving inside. Then the stride is how fast the kernel moves at a time. So let's increase the input size. So it's 7 by 7. And if the padding is 0, there is no exterior patches or basically the pixels added. Then the kernel size is 2, which is 2 by 2, and the stride is 1, so it's moving one step at a time. So now if we were to add a little bit of padding, now if I add one layer of padding on all sides, so you can see it was 7 by 7 and it's 8 by 8 on the output. But if I don't add padding, it was 7 by 7 and it became 6 by 6, so it's reducing. Now if I were to increase the kernel size to 3 by 3, it reduces even more because it's compressing a lot, 9 values to one value. So increasing the kernel size might be able to extract a lot of features at once, but the problem is you might lose the context over there. So we have to ideally keep kernel size as low as possible, but there's no point in keeping kernel size as 1 because it is not able to capture the surroundings. It's only looking at one pixel value at a time. Then stride is how often or how fast it moves. So now assume I keep 5, so it moves 5 steps at a time, both in horizontal and vertical directions. So we'll have to keep the strides also in such a way that it doesn't lose much context. So if you keep too much stride, you can see the majority of the image is not even looked at. And padding, yes. So after padding, you can still increase the kernel size. So this is what is called as hyperparameter tuning. You will have to experience different combinations of these hyperparameters to achieve the better result. So, and I would encourage, please read the definitions of all of these over here. And that's pretty much the explanation of how CNN works on a basic level. Thank you for watching.